All right, guys, we're going to start Unit 4. Unit 4 has to do with two variables. So this is the first time that we've seen two variables, okay? Everything we've been doing up until now has just been one item, one amount, a probability of one event, okay? But now we have two, well, actually, I take that back. We have seen two variables with categorical data. You know, your um, eye color and your hair color. Is there a relationship between those? Your type of driver you are and the type of vehicle you drive. Is there a relationship between those two variables? Categorical. But now we have quantitative two variables. So that's what we call bivariate. Bi meaning the two variables is two variables, quantitative variables, and we will see those visualized as a scatter plot. Okay, not a two-way table or the other kind of graphs that we've had. So take a look at what we have here. We have a situation where we've got grocery store location, their zip code, the average household income in that zip code, and then the organic vegetables offered, organic items. So this is from San Antonio, Texas, and the HEB grocery store. Okay, so we're going to explore whether there is a relationship between the neighborhood income, average household income, and its accessibility to organic items at the local grocery store. So here we go. Now we've addressed this before. Remember when we talked about our explanatory variables, our independent ones? It's that variable that we think might be predicting or having an effect on the other response variable. Okay, so how do we represent that? That's typically our x variable. And then this is also review your response variable. You know, that's the what we are measuring. It says dependent and it's related to the other one. Again, I hate to say dependent. That's always a bad thing to say because that implies a perfect relationship, a perfect correlation. If you know one thing, then that is the cause of the other, and it will always cause that amount. And so we typically don't have dependent relationships. We have relationships. All right, they measure the account. Measure the response is what we are measuring in regards to that explanatory variable. And of course, that's our y variable. So in our problem here with the grocery store, what do you think we are referencing as the explanatory variable and why? So here we have our data. So I bet you can tell that we are pondering the thought that average household income might be the variable that is impacting, having an impact on the number of organic foods at the local grocery store, the number of those items sold. Okay, so then what does that make our response? And of course, then that is those number of organic foods that the local grocery store stocks. Why do we think that there might be that relationship there? Well, if you've ever gone to the grocery store, you've noticed perhaps that the organic foods are what? They are typically higher priced. Okay, so those people who can afford that or have the luxury to be able to go for the higher quality organic items are those that have higher income. Okay, and so we think that the amount of organic items fluctuates based on the average income in that area. All right, next. So let's talk about how we can actually get the statistics for that data. Um, I do not expect you to go and put all of that information into your calculator. Okay, so I'm just going to demonstrate it for you because you'll have to take a small amount of data on your homework and be able to compute the summary statistics. So let's take a look. I have gone to Stat Edit, And look here, I put in list 1 that list of all of those salaries or the average household incomes. Okay. And then I put in list 2 the number of organic food items that that local grocery store stocks. Okay. So that was a lot of data there. So I don't expect you to put all of that in, but you can follow along. Now we need to calculate, and we're going to calculate to the linearity, the linear relationship. So hopefully you remember from your last math class that did functions, Algebra 1, Algebra 2, pre-calculus. You're going to stat, and then you're going to arrow over to calc, okay? And then here we go. We're going to reference the linear relationship here at first. So linear regression, number 4. So if this menu does not show up, then you could just have your calculator defaults to L1 as the X list and L2 as the Y list. Okay. So we're just going to go ahead and go calculate that. And here is the information we get. Okay. Now, yours very possibly does not have this R squared and this R show up. And we need those items. So there are 2 ways that you can get this to happen. So you've got to know how to do this on your particular calculator. If you have a more current operating system on your calculator, then you will be able to do what's called turn the diagnostics on. In fact, I think I'm going to write that in here. We need to, in order to get those things, we need to turn the diagnostics on. And so that's what we're going to do. Turn diagnostics on to get the R and the R squared. Okay. And to get the R squared. Now, let's go ahead then and show you how to do that. There are 2 ways. And again, if you have an updated operating system, you've got it easy. So let's see where that's located. Here, under mode, you just press mode. And so you can see this menu of items. This right here, FYI, Stat Wizards, if that is turned on, that's how you get that menu of items so that it tells you what to plug in. Like what do you want your X variable to be? L1. What do you want your Y variable to be? L2. Okay, but this is right here. Look, stat diagnostics. And if you are a regular calculator clearer, stat calc linreg or 712, whatever, stat calc 712, then guess what? Every single time you need to do this, you're going to have to come back to your mode and turn your stat diagnostics on because the calculator defaults to turning it off. So here we go, on. Now, if you do not have this handy dandy updated operating system, then look at what you're going to have to do. There is a list, an alphabetical list of every function the calculator has in the catalog. Look down there at the bottom. Catalog is above the 0. So to get to that above the 0, we're going to go second and 0. Second 0 gives us that alphabetical list of everything. And I need to go to the D portion of the alphabet, letter D, for diagnostics. Well, if you sit there and scroll down, it is going to take a long time because there is a lot of functions that the calculator does between A and D. So I usually come over here. If you look really closely, I think above this button that says x to the negative 1 is the letter D. So it's in my calculator, it's in green. So that means alpha. I need to push alpha. So I go alpha x to the negative 1. And if I do that, if I go alpha x to the negative 1, there we go. Now it takes me to the letter D portion of the alphabet. And so then I can now I'm closer to where I needed to be. And I'm going to arrow on down to di. Oh, by the way, if you were in pre-calculus, there's where you could detect some asymptotes. And so I'm going to do diagnostics on. So I'm going to hit enter. And then that's not done it yet. I now have to press enter again so that it says done. And now when you go recalculate, you go stat, calc, number 4, calculate, or calculate. Then there it is, r and r squared. Okay, that's the only time I'm going to go through that process. So if you can't ever get r and r squared, turn your diagnostics on. All right, here we go. So there's our information. Let's take a look at that here. So there it is. The slope. Okay, so look at this slope. It's good that I'm going to kind of go through some weird numbers so that we can kind of discuss how to go through those weird numbers. Most of the time we don't get strange numbers like this, okay? But here we do. So it's 9.59. That is not the slope. It's, look at the end, times 10 to the negative 4th. A lot of times that doesn't happen typically. So we're going to do, so that means it's like scientific notation. I need to move the decimal 4 times to the left. So I'm going to do that. And I'm always going to do to 2 significant digits, 2 sig figs behind the decimal. So that would be 0.00096. The y-intercept is that negative 14.79. So therefore, my equation in context of this problem is this. So when you are asked to write the equation of the line on the homework, you have to do it in context. So look, the y variable is the number of organic foods equals 0.00096 times, that's the slope, times the average monthly income minus 14.79. Now, one last thing. We are approaching this thing where our line that we have, I'll show you a picture of what's happening. Our line that we have is, the average of all those dots. It's going right down there in the middle. But it is just approximating what we can predict. It is not what actually happens. So if you just put that the number of organic foods equals this equation, you are saying that for a fact, if I tell you the monthly income, then you can tell me the number of organic foods. And that is not the case. I can tell you approximately what the number of organic foods are. In fact, if you take a look at this line, how many dots are exactly on that line? Maybe 1, maybe 2. I don't even think there is that. Therefore, we have this very important, absolutely essential thing called a prediction hat. That is this. It's like your sorting hat in Harry Potter. This prediction hat says the predicted number of organic foods follows this line. That's not actually what's going to definitely happen, but that is going to tell me approximately the predicted number of organic foods. You are wrong if you tell me in the exact number of organic foods, because you can't. You're telling me the predicted. All right. Now we're going to get into interpreting the equation, the parameters of that equation of the line. So here we go. We're going to interpret the slope. Well, that slope is pretty weird. 0.00096. Okay. So let's talk about kind of what's happening just in general with slope. Okay. And slope, remember, you go over and you go up, and you go over and you go up, and you go over and you go up. Usually we say, like, for every time you go over 1, then you go up this much of the y direction. Over 1 in the x, up in the y. So look, here is my attempt at helping you remember how to interpret the slope. There were several years in a row that the AP test had the problems. Actually, there were 2 years in a row, 2017 and 2018, where problem number 1, the very first question was giving you information just like this, and it said, number 1, A, interpret the slope. And then number 1B said, interpret the y-intercept. And so that's exactly what we're learning how to do. Interpret the slope, interpret the slope, interpret the slope, interpret the slope, interpret the slope. For every 1 increase in the x, the predicted y, it does this. Interpret the slope, interpret the slope, interpret the slope, interpret the slope, interpret the slope. All right, so let's do it here. Well, here's an example. For every 1 degree increase in the temperature, the predicted energy use increases. The predicted energy use, not the actual energy use. It's predicted that the energy use increases 256. Okay, so this is a weird L number, 0.00096. So here's like, I have it real small. Here's technically how that would play out in the song. For every $1 increase in the average monthly income, the predicted number of organic foods at the local grocery store increases by 0.00096. You could get by with that, okay? Because that is literally what's happening. But in context of the problem, that's very awkward. All right. So, and normally we don't have this awkwardness, okay? But that's okay. I'm going to show you how to work through this weird situation of this slope of 0.00096. Well, I'm thinking I would like to as easily like get close to a whole number amount of items. So, in my brain, I think that if I go like 0.00096 times, I think 10,000 is going to get me pretty close to a whole number amount of items because it's that little of a decimal. And there it is, 9.6. 9.6 items predicted to increase that much. That sounds a little bit more realistic and natural in context of this problem. So, how about this? See how this sounds for you. For every $10,000 increase in the average monthly income, the predicted number of organic foods sold at the local grocery store increases by 9.6 items. And it's okay to say 9.6 items only because we said the predicted. So that means it's not actually what's happening, but that's what is approximately going to happen. Now, here is the other way, another way you could say something similar to this. Let me do this little guy right here. For every $10,000 increase, look, it says for every $10,000 increase in the average monthly income. Now, look, I'm not going to use the word predicted, but I'm going to say about. The number of organic foods sold at the local grocery store increases about 9.6 items. So you might like that one better. You must use either predicted number of Y things or the actual number of Y things increase about this much. You use predicted or about. You cannot do both. You cannot say it's predicted to increase about this much. No, the prediction line tells you what it's increasing. Okay, or you say it will increase about this much. You don't do both, one or the other. Here's some other optional ways. If I multiplied by 100,000 instead of 10,000, then for every $100,000 increase in the average monthly income, the number of organic foods sold at the local grocery store is predicted to increase by 96 items. Because the number of items didn't really seem to be in that range, and 100,000 just kind of seemed to be increasing by 100,000 just seemed to be really out of the span of the scope of things. I thought just increasing by 10,000 seemed to be a more normal thing to increase by. So anyway, so that's why I don't prefer that one. I think that one's a little less, but super important to only use predicted or about, not both. Okay, Next thing, here we go. Now let's interpret the Y-intercept. Goes to the wrecking ball. Interpret the Y-intercept. Okay, so let's take a look at where that is on our graph. If we say, look at this graph, then our Y-intercept is right there. Our Y-intercept is always happening when this X value is 0. That's the key to this problem. Now, this actually, I think if I was to look at my window that this calculator gives me, I kind of am thinking that this window does not show me when X is 0. I think if I looked at the window, this isn't at X equaling 0 yet. How do I know that? Because the Y-intercept is negative. So see, I don't think I'm actually at 0 yet. I think this would extend out here. It'd probably be keeping on going about like this. And so then probably you'd have here's where your origin is, probably somewhere like that. Okay, and so then here's your Y-intercept at negative 14.97 right there in that area. Okay, so let's do it. So interpret the Y-intercept. It happens when the X is 0. Interpret the Y-intercept. It happens when the X is 0. And it tells me what the Y is predicted to be. Again, not what's actually happening, because as you're going to see, sometimes what's predicted doesn't even make sense really in context of the problem. Look here. Our Y-intercept was negative 14.79. You know what that says? That when the average monthly income, when the X is 0, when the average monthly income is 0, then our number of organic foods is predicted to be negative 14.79. Does that make sense in context of the problem having negative amounts of organic foods? No. And so we'll learn about why it doesn't make sense at a later time. It has to do with this thing called extrapolation, and we'll talk about that later. But we just are kind of anchoring on interpreting that Y-intercept. It happens when the X is 0. So interpret the Y-intercept. It happens when the X is 0. The predicted Y is this, and it often does not make sense. It often does not make sense. Okay, and that's because we have this thing extrapolation, which we'll talk about later. So, interpret the Y-intercept. When the average monthly income is $0, the predicted number of organic foods sold at the local grocery store is negative 14.79. Okay, which doesn't make sense. Again, do not use predicted and about. Okay, that video was long enough, so I'm going to let you take a little break there. You might even go stop and try that on your homework if you wanted to. And then we'll do the next video, which takes into these new ideas, the R, the correlation coefficient of correlation coefficient, and coefficient of determination. Okay, so I'll pause this video here, and you can turn to the next one for the next part.